Every day, large amounts of information are published in the form of news, posts in social networks, scientific articles, and more. It is difficult for us humans, and even computers, to try to make sense of it all. Not only the amount of data that is produced daily is massive, language can be ambiguous and dynamic. It would be useful if instead of raw text, we could represent knowledge as a collection of entities like people, countries, and buildings, in a way that connections between these entities express what we know about the world. This representation is known as a knowledge graph, and it's a technology that is used to turn large amounts of data from different sources into a form that computers can process and analyze efficiently. My name is Daniel Dassa, and I'm a PhD student at the Vrije Universiteit Amsterdam and the University of Amsterdam. And in this video, I will be presenting the work of our lab on using artificial intelligence for knowledge graphs. Knowledge graphs are increasingly being adopted in industry to power applications like search engines and recommender systems. However, even if we do a really good job at maintaining and updating a knowledge graph, it is likely that at some point it will be incomplete. What happens if we want to answer a question using an incomplete knowledge graph? Take, for example, this small knowledge graph. This graph allows us to answer a question like, what places has Bill visited? A graph database would use this information in the graph to return the correct answer, the Eiffel Tower. But what if we have another question like, is Alice a person? The graph tells us that Bill and Bob belong to the class person, but this information is not there for Alice, so we cannot get the answer. In our work, we have used machine learning to exploit patterns in the knowledge graph that would enable us to answer a question even if the graph is incomplete. Intuitively, in our example, we can see that, like Alice, Bill has visited the Eiffel Tower and Bob is a friend of Alice, so it is likely that Alice belongs to the person class. One way to achieve this is by associating a vector to each entity and relation in the knowledge graph. These representations are also known as embeddings, and we can design them such that operations with these vectors reflect the information contained in the graph. At ICT Open, we present our work on using embeddings to answer complex queries. As opposed to a simple query like, what places has Alice visited, that would require looking at a path of length 1, complex queries require considering larger neighborhoods in the graph. An example would be, what is a place that both Alice and Bill have visited? In our first line of work, we propose to break down complex queries into simpler ones. Here, we break down the query into two that ask for places that Alice and Bill have visited. We answer them separately using our embeddings, and then we merge the result. In spite of their flexibility, we can make knowledge graphs more expressive by adding extra information to facts. For instance, statements that describe places that Alice visited can be made more precise by specifying if they were done via a certain company. For example, we can specify that Alice visited the Eiffel Tower via the Paris Tours company. These additional details that we can attach to statements are known as qualifiers, and knowledge graphs containing them are called hyper-relational knowledge graphs. In our second line of work, we have designed a framework for answering queries over these hyper-relational knowledge graphs. It is based on a neural network that encodes the queries and ranks potential answers to them. In our experiments, we find that using the qualifier information and the right neural network allows us to produce more accurate results. We hope that you join us at ICT Open to continue the discussion on using machine learning to exploit the wealth of information in knowledge graphs.